Let me share my screen here. Can you guys see my screen?
Yes.
Okay, great. Yeah, so today I'll give you guys a little bit of overview of the new capabilities that we have at Flexcompute. Um, and are you guys already using our Tidy 3D solver, or that's also something new for you guys?
We've been using yeah, those tidy 3D credits. Thanks a lot
Oh,
from
okay.
last year.
That's great. Oh, so that makes it a lot easier. So you are familiar with our platform. That's fantastic. Yeah. So if you're designing a real chip, component level simulations like FTTD is one of the things you have to do, but there are a lot of other things you're typically trying to do when you design a real chip, right? You might be doing optical simulations, which includes mode, EME, inverse design. FTTD. You might be doing RF simulations of transmission lines, interconnect, signal integrity. You might be doing thermal simulations, both at the component level and also at the module level. And then if you're designing active devices, which in most cases, most of the devices that people use in for practical applications are going to be active devices, there you might need electro-optic simulation, charge simulations, and maybe even thermal simulations. And so currently, that's one of the things as a photonic designer myself, this was one of a big pain point, and there isn't really a unified platform in for photonics to kind of design your photonics chip from scratch. You usually have to kind of juggle between multiple tools, layout tools, simulation tools, um, and then verification tools, and then you have to figure out how to turn that into a design that you can manufacture. So there's a bunch of hoops that you have to jump to get to your final design, and that's what we are hoping to solve with Photon Forge, to provide you a seamless interface where you can do end-to-end photonic chip design. Um, and we are really well positioned to do this because, we've been building a lot of different solvers, particularly, these GPU accelerated solvers, which I guess you have already used and you've kind of seen the speed advantage, like with the FTTD solver. We have our mode solver also. We also have heat solver that's already been, released, and then chart solver will be released basically before Photonics West. And so we have a lot of these different solvers that can solve very different physics. And Photon Forge allows you to, actually do your design, do layout, do circuit simulation, and also build compact model using these very different solvers. Um, and just to zoom out a little bit and talk a little bit about Flexcompute, I know you guys are already using Tidy 3D, but we do have a lot of different solvers that are solving very different problems from related to aircraft wing design all the way to interconnect simulations. And the reason I bring this up is, we have expertise simulating very different types of physics, all the way from fluid dynamics to RF acoustics and charge solver. So what that allows us to do is build this platform that's kind of seamless in terms of usability. I'm not going to go over Tidy 3D here because you guys are already familiar with it. Maybe you guys are also, I don't know if you're using inverse design capabilities, um, but the things that are kind of, newer are our RF and microwave capabilities. And today I'll just kind of focus a little bit on Photon Forge. So the way you interact with Photon Forge is very similar to how you're used to interacting with Tidy 3D. So you can either use our Python interface or you can use our web interface. Here's an example of what our web interface looks like, and we make it super easy for people to go and access our software. So all you need to do is do tidy3d.simulation.cloud, and once you have an account, you can just click Photon Forge and get started that way. Um, it is both a viewer and an editor, where you can not just edit your GDS files or load Foundry PDKs, but you can also export GDS files and run simulations directly from this interface. So it's designed for users who want to do some quick simulations. Um, but the but where we have a lot more capabilities is through our Python API and Python interface. Um, it's also incredibly easy to set up, just like Tidy3D. You just do pip install Photon Forge, and you can start building, relatively complex layouts. Like this layout, for instance, was built in Photon Forge. Um, so if you talk a little bit about layout, traditionally, people were doing photonics layout like, geometry by geometry. I think that makes it a lot harder to kind of scale to larger complex circuits. So a better approach is this kind of schematics driven or layout driven design. And in Photon Forge, that's very easy. You build individual components and then you're basically connecting them with auto routing. And then you kind of assign various types of ports that you can use to couple light in and out of your system. And once you define these 2D layouts, Photon Forge makes it very easy to go to actual 3D geometries because all the information that's contained in your fabrication process or a foundry we're calling technology is contained within Photon Forge. So um, and to load that foundry technology, it's in this case, it's as simple as just saying, Photon Forge, load this basic technology, and you can use a lot of parametric components. They're called P cells typically in photonics, or even electronics. And we have a lot of these parametric components. We also have a lot of basic geometry functions, so you can draw any GDS layout. Um, but the nice thing is once you build your component, running a simulation or in this case, getting an S matrix for that component is as simple as just saying component.S matrix and giving it a frequency range. And basically with some model for your component, and in this case, it's building an FTTD model to get that scattering parameter for this component. But it can be analytical model, it can be model based from experimental data, it can be any custom model. And so with models and ports defined for your photonic devices, you can build pretty complicated circuits and look at how they perform. Um, yeah, here's a example showing how we can use Photon Forge to build. This is a dual polarization IQ modulator. Um, yeah, so it knows, because of the technology setup, it knows how to go from 2D layouts to 3D simulations in basically one line. So you avoid a lot of setup that you typically have to do with Tidy 3D if you're kind of starting by building all the geometries from scratch. The other key part is, we work with a lot of foundries to kind of build all this foundry tech stack. So the mask layers, layer thicknesses, all the different components that the foundry offers, and we provide that to you through Photon Forge. So you can kind of start building your actual circuit design, and you don't have to start from looking at the PDK document and trying to build the geometry. And so you can easily seamlessly go from layout file to 3D electromagnetic simulations or other types of simulations like circuit simulations, and then build a compact model for your component. These are some of the foundries that we already work with: Tower, IMEC, Fraunhofer, Ligantech, AIM Photonics, SciEpic. And we've chosen these just to show that these we can work across very different material platforms, all the way from silicon to thin-film lithium niobate. And once that technology is loaded in our platform, when you do any type of drawing, you can quickly inspect what that geometry looks like, what that cross section looks like. The the other key part of doing photonic design is actually taking into account manufacturing variability, process variations. So your thickness of your silicon layer might change, your edge depth might change, and typically from a foundry you get some mean value and then some standard deviation about that critical dimension. And all that information is stored in this technology file in Photon Forge. And once you build your geometry, you can run S matrix and get your idealized design, or you can just say S matrix Monte Carlo, and you would just run through all the different variables, all the variability, and give you a sense of, okay, what type of experimental variation you would expect to see when you actually tape out this device. Um, um, with Photon Forge, because we're still in this process of building a lot of new functionalities, we try to continuously update our documentation. We work closely with a lot of customers to kind of build notebooks specific to their use case. And of course, we help them kind of build any simulations that they want to do. So please check out our documentation, which is kind of listed here in this link. Um, the other big piece is, there's a lot to do to get to this kind of goal of trying to be an end-to-end design platform. And some of the things that we had on our timeline was actually doing time domain simulations. That's pretty important because if you want to simulate any kind of active devices, you want to be able to put, time domain signals like modulators, uh, and so on. And so this is now implemented in Photon Forge. So you can take an S matrix for a component, turn that into a time domain model and time step, and you can look at how signals propagate in your circuit. The other key piece that we're going to be working on is actually integrating models for lasers and semiconductor optical amplifiers, because at the end of the day, your photonic chip does not work if you don't have laser sources or amplifiers, right? So this is something that we're going to be working on to build more accurate models so that you can really simulate your chip with also sources. That's a pretty high level overview before I jump into some actual demos, but I'll pause here and then, if you guys have any questions, just let me know.
Very cool. On the laser part, how do you model the lasers?
There are a lot of different ways of doing it. I mean, zeroth order is, especially if you have experimental data, you just, load the frequency response and then you kind of use that as an input to your kind of system. More complicated is actually you start with like rate equation based approach, and then after that you do, 1D traveling wave approach. There's a lot of actual physics to be implemented there, if you want to build more and more accurate models.
Right. I just wasn't sure if those are what do you call them? Phenomenological models or
That's right. Yeah, so one of the nice things about Photon Forge is that you can combine like different types of model. You're not restricted to one type of model. You can use analytical models. You can use, yeah, you can use models like that are going to be much more efficient um, than trying to solve everything from first principles, because that's also that's a separate thing, right?
right. I see.
Yeah, for SOAs and lasers, we'll probably start with the traveling wave model. I think that usually that's pretty accurate at modeling laser dynamics, like noise and stuff like that. So
And what exactly do you mean by emulator? Um,
yeah, that's that's awesome. Yeah, I love this emulator term because what it is when you take a chip, like what you want is a platform where you can kind of just put together everything and emulate what that real device is going to look like. I put a laser here, I put a chip here. It's like almost like doing an experiment, right? So it's not like a real device you don't fabricate, but you already kind of get a sense of what the real performance looks like. um that's kind of what I mean by emulator. It's actually a very common term in in more like the electronics world, where you can basically emulate like an ASIC. Like if you're designing an ASIC, like you can basically emulate that on another supercomputer and see, okay, if I were to put this combination of transistors, what would my output look like? This is kind of like trying to achieve the same thing, where if you could just simulate everything before you actually fabricate, then that would be pretty amazing.
I see. And this is at the um chip level, right? There's no package level. Uh, like you're not modeling like the coupling of from like the fiber into your chip, right?
You can. That model can just be FTTD model. So you can launch, I guess, maybe I'll sh there's an image here. Um, you see this image with grading coupler here?
Oh, okay, I see.
So you can have a model for this grading coupler or whatever edge coupler. And so you will simulate, you'll have a model for how the coupling losses and all that stuff depend. If you had a wire bond, if you could do electrical simulation, you can build a model for that. So it's pretty general concept.
Do you have any questions, Bora, Chloe? Chloe makes VCSELs and Bora makes well, actually, what devices do you make these days, Bora?
Hi, I'm fourth year grad student. I was also curious about the word meaning of emulator, which was cool. Um,
Well,
yeah,
I'm glad people like it. That's great.
yeah. My advisor recently started a new project which involved the Photonic Integrated Circuit.
Yep.
So that's why I was curious, was interesting in joining this
Yeah, so
yeah
so
meeting. But I just wanted to say that I don't have really great background knowledge, so I'm just learning here.
Mhm. Yeah, no, that this is great. I mean, that's another, there are a lot of, foundries that just that not only make um silicon photonics chips, right? Photonic integrated chips. There's a lot of people who are making detector, there are people making lasers, amplifiers, like VCSELs and all sorts of stuff. And the question is the real device that actually, gets used or used in industry actually combines a lot of those different platforms. One maybe 3.5. Now people are talking about heterogeneous integration. You might have silicon photonics. And the question is, right now there isn't a platform where you can kind of simulate all that, the real performance at the system level. But I think with what we're building here, should be able to incorporate a lot of those effects and try to get closer to simulating what a real device would look like.
Yeah, that's good to know. So yeah, we're basically doing 3.5 on silicon.
Yeah.
So yeah, it's good to know that this model is just like simulating the
Yeah.
all on in one chip.
Yeah, exactly. Yeah, there are a lot of foundries that are working on this exact
Mhm.
problem of heterogeneous integration. And a lot of what we're trying to do is also kind of motivated by real problems in the industry that these foundries have shared with us. So yeah, so these things will be released in the later half of the year.
Yep.
Actually, I do have one more question. So, how would you incorporate photonic water bonds in this framework?
Well, I mean, it's photonic wire bonds are just you just run an FTTD simulation, right? You take whatever your fiber, and then you take I guess the tricky thing there with the photonic wire bond is that it's like a 3D curved geometry, so you want to make sure you mesh very well. Usually these FTTD simulations, because of the rectangular grid, right, they work really well for these planar circuits. But once you start doing things like photonic wire bonds, where you have curved things and then you have narrow tapers at the end of the waveguide where you're connecting it, you just need to mesh it a lot. But then once you mesh it a lot, again, you have input port, which is your fiber, the output port, which is your waveguide. And then you just build an S parameter for that. And that's your model.
Yeah, that's fair.
Yeah. All right. So should I just quickly go through a few demos, if you guys are interested? I don't know what layout tools do you guys use to do your layout and fabrication and stuff like that?
I usually just use like K-layout and GDS Factory.
Okay.
Yeah.
Oh, that's great. So you're familiar with Judo. Yeah, that's fantastic. Yeah. So the layout part here is basically, well, it's basically like GDS Factory. It's implemented with like a C++ backend. If you're familiar with that type of approach of doing layout, then should be easy for you. Um, but where it's different is in all the integrations that we offer to our solvers. So it makes it very, very easy to go from your layout to simulations and back and forth. And we have, if you're running like more like simulations at the circuit level, if you're not just doing like a component design, but more like you're doing system level simulations, then you can run both frequency and time domain simulations through this interface. All right, let me just show you. So So in this demo, I'll quickly walk through how you would load PDK components, um, or even like custom components. Like you might have your components already created in some GDS file, and I'll show you how to run some simulations directly from Photon Forge, um, and then take those components and build a circuit. Like I'll build a very simple circuit, which is just a Mach-Zehnder modulator, and then show you how to run circuit simulations on once that modulator is defined. So the core, actually, I'm going to start showing these. So the core concept in Photon Forge is just there's actually only like 3 or 4 concepts. One is that everything that you draw, you eventually treat that as a component, right? A component could be a straight waveguide, coupler, even the big circuits are just a component. Um, each component needs to have some technology. Sometimes if you're just using silicon on insulator, then your technology is very simple. You just have silicon waveguide, oxide, and silicon substrate, right? If you're using some complicated process where you have metals and you have doping, then you have a slightly more complicated technology. You might have silicon nitride on silicon and 3,5s and all sorts of stuff. And then the other concept is ports. So you have your component, light enters and exits that component, and so you have ports, right? And uh, and then the other thing is what type of model are you going to use to model this component? For some passive components, FTTD would be a great model for that, right? If you have a really long waveguide, probably doesn't make sense to use FTTD model because you probably, will spend a lot of time and go through a lot of credits to just, calculate that, okay, you're just changing the phase, as you go from one end to another. So in that case, you can use analytical models where you look at like the group index or the effective index of your optical waveguide and use that for propagation. So with these kind of core concepts, let me show you how uh, you would implement some simulations. Okay, so the first thing is I'll just show you how to use some open source PDK. So you import Photon Forge and you import Tidy3 just like you import any other Python package. You can also import PDKs. And then you just say, okay, this is my PDK and I'm going to use the E-beam technology. And then I'm going to set that as my default technology. With that, there's a lot of other settings you can set. You can kind of ignore this like mesh refinement and whether I want to show SVGs or not. And there are a bunch of other config settings. But the key thing is to define your wavelength and then what wavelength range you're interested in. After that, I'm not going to run through all of these, but at least I want to show you. You can just say, okay, in this PDK, what are the different components that are already available for me to use? And you can just say, okay, I'll just look at one of the components, the E-beam Y splitter, right? You can also, I don't know, let's look at some other, okay, crossing. Okay, there's already a crossing that's defined. And I'll go back to this one because we're going to be building an MTM. So each component, when you load it up, you can also look at the models that are already part of that component and then also ports. And typically you probably heard of the term compact model or something like that in other simulations. That's basically that. So you have some model for your component and you have some ports. With that information and the fact that you define technology stack, you can already start looking at the cross section. So in this case, I'm just plotting, what if I were to go at the x equals 5 plane, what would I see, right? So if I were to go to x equals 0, you see that waveguides are getting closer. If I do z equals 0, you see the waveguide. So you can see the whole cross section. It's really simple, but when you have very complicated geometry, it's really nice to visualize how that's going to look like when you do the fab. So once you have ports and once you have models, then creating or getting an S matrix for that component is as simple as just saying your component dot S matrix and just give it the frequency range. And then what Photon Forge, I'm not going to run it, but Photon Forge will do is you will kind of automatically look at the ports and look at the technology stack and build like, different simulation it needs to fully characterize that component. And then once that S matrix is calculated, you can just plot the S matrix and you see that, okay, it's, should be 3 dB ideally, but there's a little bit of loss, like 0.14 dB because of scattering and all that stuff. So that's one way where we integrate the layout part directly to FTTD solver. Another example is, let's say you wanted to quickly look at the ports and look at what are the modes that are supported, right? So you can just take the Y splitter, take the port 0, P0, so this port, and then just say export that to a tidy 3D mode solver. And then you'll see, okay, I want to do this at this frequency and just mesh refinement, and you solve for that mode. And you see that, okay, the effective index of that mode is around 2.45. Here's the group index. I didn't turn group index equals true, but this is kind of something you're probably already familiar with if you're using tidy 3D. And you can, plot fields. All the things you can do in tidy 3D, you can do it here, but it's just a little bit more streamlined because we know what that, cross section or the geometry looks like. The other, important piece is you might have, GDS files of components that you already made or optimized. You can simply just load that. You can say load layout. Let's say this is a thermal optic phase shifter, right? Load the GDS file. You can see what that looks like. But when you save your components as GDS file, you've lost a lot of information about ports and models because it's just a geometry file. But in Photon Forge, you have really nice functions that allows you to detect different ports, optical ports. And the reason you can do that is because each PDK will come up with, okay, here are the different standard waveguides for this at 1550 nanometer. In this case, it's a 500 nanometer waveguide. And because there's no model for this component, and because this is a very long, let's say, heater, I'm going to add what we call the waveguide model. It's essentially an analytical model that will do a mode solving at the ports and figure out the the effective index and use that to calculate S parameter. But it's as simple as just saying for this waveguide section, just use analytical model, and Photon Forge will take care of the rest. So once you have your components, individual components like this, phase shifter, Y splitter, you can start to build your circuit, right? I mean, this is a very simple toy example, but it kind of shows all the important pieces. Um, there's this concept of kind of doing the schematic-driven layout where you kind of put components or instances of various components in your canvas. So in this case, I'm putting one Y splitter for the input, another Y splitter for the output. In the output one, I'm placing it some distance away and kind of rotating it by 180 degrees. And then I'm using a lot of auto routing functionalities in Photon Forge to just kind of automatically connect. So in this case, I'm saying, okay, port 2 of Y in, connect that to port 0 of the power of the phase shifter. And then you say, okay, finally, these are the ports. And this is where all the magic happens, which is at the end, you have connected all these components. Some of them, this one has analytical model, this one has FTTD model. But how do you want to simulate the final device? You could say, if you said FTTD model, you would try to run a full big FTTD simulation. But instead, what you can do is circuit model. When you do circuit model, Photon Forge will automatically go and look at all these components and try to figure out, okay, do I have S matrix for this? Do I have S matrix for this? Or what do I need to do to calculate the S matrix for that? And automatically execute that and then give you a final S matrix. So you can, convert, once you have a component, you can always say write layout or write GDS to go from component to basically the GDS file you would use to fabricate. But the best part is because you returned a component for using this function, and you can see this is already a parametric function, right? Now calculating the S matrix for this component is again as simple as saying for this whole circuit, just give me an S matrix. So it's dramatically simplified, right? Yeah, so that's a pretty high level and very quick overview of the workflow of how you would, do layout and how you would do circuit simulation, how you would load GDS files in Photon Forge. Do you guys have any questions? I'm hearing silence.
Uh, Nikita put something in the group chat.
Oh, there is. Sorry, let me just. I can't. Chat. Okay, so let me try to.
Uh, I'll just read it out.
Yeah, please. That'd be great.
Yeah,
Oh, yeah, I see it,
yeah.
but yeah,
You mentioned that there are analytical models for straight waveguides and similarly simple components, but
yeah,
this routing between components have can have different curves that are determined algorithmically. So
yeah.
how does Photon Forge handle those routing waveguides in
That,
this example set?
that's a really good question. In fact, so ideally, right, if you start having curves and bends, like you don't know because if the bends are tight, then you might have loss and all this stuff. So ideally, you would want to run FTTD simulations. Um, but you also have this thing where in most, when you're doing most design, you kind of already know, okay, this is my minimum bending radius, and most people, will say, okay, in this platform, don't go, don't make your waveguides have bend that's tighter than this. So we let user kind of override. You can kind of override what type of model there's like actually if I show you so just like instances, you can kind of override the model for that component and say, okay, for this component, just use FTTD model. Um, but typically when you're making routes, the assumption is that you're not making routes that have such tight bends that you're going to get lost. So the default option is actually using analytical model. So it does the mode calculation and uses that, but you can override that if you think that you're going to be using tighter bends in some cases. Does that answer your question?
Yeah, it makes sense for us. Thanks.
Yep. Yeah, and the layout part for Photon Forge is free for you guys to use, so you can just do pip install Photon Forge and just get started right away. It's only when you need to run simulations or circuit simulations that you'll need a Photon Forge license.
Um, when you add like layers such as like different materials,
Yeah,
this library has the properties of these layers. Like I guess I'm curious like how
yeah.
wide range like this.
Actually, I'll show you. This is
Yeah.
great. That's why I have this custom PDK. It's so this is another thing that we have tried really hard to simplify, and I think this is, this is always a problem when you use other softwares I've used all these softwares like in the past, and the setting up a technology and PDKs always takes a lot of efforts, multiple files, a lot of going on. In Photon Forge, we kind of simplified that dramatically to basically it's another class. It's a technology class. And in this case, I'm making a thin-film lithium niobate PDK in just like a few lines you can see here. All I need to do is I need to say, okay, what are the different layers? Okay, so GDS layer 10 is your strip waveguide layer for thin-film lithium niobate. There's a slab layer. This is different GDS, and you can this is the color or whatever. Um, there's a lot of input parameters, right? You typically your thickness of your silicon layer is this much. Your edge depth is whatever. Silicon would be like zero point 0.2, edge depth would be 0.1, box thickness is 2, cladding is something, and you just come up with these numbers. This is like your function, right? And then you just say, I need to extrude. So this is where all the magic happens. You're just saying, I'm going to extrude this layer from 0 to some thickness with some sidewall angle, and this is the material. And the material is defined using, if you're used to Tidy3D already, Tidy3D has a bunch of material things. So you can either use the Tidy3D medium or you can just kind of override. In this case, I'm just Because it's an anisotropic medium, I'm overriding and putting in the parameters by hand. So that's essentially it. So you just need the layers and extrusions. And the ports are kind of optional. This was what I was talking about earlier. Ports are optional. They're not needed as a part of technology. You can always add them later. But typically if a Foundry PDK says, okay, typically if you want your waveguide losses to be low, make sure your waveguides are at least this, 1 micron wide or something like that. Then you can say, okay, uh, this port has some width and some Z dimension, right? It supports some number of modes. This is roughly the target effective index of that port. And then here's the layer. So it's basically on layer 10, which is the strip waveguide layer. That's it. That's all you need to create a technology. So it's incredibly simple to create your own technology. And when you create technology like this, so in this case, you can see here, um, you can visualize the cross section once you make your device, and yeah.
Yeah. I guess this kind of thing make me like have a follow questions.
Yep.
I guess the answer like really varies by model, but how long does it usually take to just simulate this kind of type of simulation?
That's great. Yeah, so if the type of the time depends very dramatic
Yeah, yeah.
on what model you use. So if you use FTTD model for everything, right, especially for very long or big components, then it will take a little bit long because you're running tidy 3D simulations. Tidy 3D is already fast, right? Like 500x faster, but you still don't want to run if you have a 1 centimeter waveguide, you don't want to run FTTD simulations because that would take forever. The mode simulations are pretty quick. Circuit simulations are almost instantaneous, and they take you can't even they take less than a second. So as you enter, you'll already see it. Um, so it really depends on the type of model you're using. But usually, if you do circuit simulations, it's going to be much faster um, than running. Maybe this tunable heater is this actually. I don't know if it's been run before, but um, yeah, it's actually not running, so I would have to run it again. But once you build all your models for your components, it's way faster because the circuit simulations are essentially just doing matrix multiplication.
I see. Thank you.
Yep. Where am I? I'm lost here. All right. Yeah, those are all great questions, like how to create technology, what happens to routing. All right. If we have no questions, I'll pass it over to Adam.
Thanks, Prash.
Of course.
So, I guess if there's no other questions, as Prash said, we'll wrap this up and I will send over the recording of today's session to you, Chloe, so that you guys can post that um, throughout. If others are interested in maybe learning more, please let us know. And as Prash said, you can already use Photon Forge with your Tidy 3D license as long as you're part of a university or education license structure, which you guys are obviously. So you can start using Photon Forge today if you'd like. It is included. And then if you guys want to learn more or have more of a deeper dive tutorial to do more specific things, just let us know and we can set up time for us to go through that so that you guys get more comfortable. Does that sound good?
Yeah, that sounds good. Actually, I have one last question. How mature are the thermal and acoustic aspects that you mentioned briefly?
Thermal is you can start doing so if you go to 3D heat simulation, yeah, you can see here, right? There's some examples, so you can already play with it. So you can do relatively complex structures with this workflow. Acoustic, I think the acoustic is more designed for maybe aircraft simulations for now, but I don't know if Mark, you're here, but maybe isn't Mark here, or maybe he left. I think that's more focused on it's not acoustic. Right now, at least, it's focused on acoustics for like cars and airplanes and stuff like that.
Oh, okay. I see. I assume you meant like thermal optics or acousto optics.
Oh, no, not acoustic.
Okay.
Acoustic optic
Okay.
market size is probably pretty small.
Okay. Yeah. That makes sense. Yeah. I was just curious since you put it
Yeah.
on the intro
Yeah,
slide.
actually, there
Okay.
aren't that many solvers that can do. A large part of my work in grad school was doing acousto optics, so there aren't that many tools to do that. Basically, you can use console, and that's basically it.
I see. Okay. Yeah.
Okay. All right, I will send over the recording as soon as possible. And yeah, again, please reach out to us if you guys have any other questions or want to do a deeper dive into more specific things.